Hey digital crew. So today we are going to be looking at asteroids, and then we're going to ask ourselves, why is it that Earth and the other planets don't just fly out into the solar system? Why are they stuck where they currently are in their orbits? So let's start off with this. This is an asteroid. So these are irregularly shaped rocky objects with diameters less than 1 kilometer. And well, a kilometer is just a little bit over half a mile. So it might not seem huge in comparison to the sun or to planets, but it's still pretty big. And this stuff is flying around up in space, as we'll talk about in a moment. So we're a little bit afraid of what might happen if one of these bigger ones ends up colliding with us. But more on that in a moment. Leftover debris from the formation of the solar system, anything that didn't form into the sun or into the planets or into the moons, was left as this rocky material known as these asteroids. And we'll see that there are a few different places that they exist. They revolve around the sun the same as planets, so they are not just sitting there, they are actually moving. Asteroid belt between Mars and Jupiter has thousands of asteroids. It's quite large, and potentially if all those asteroids had done what the planets did, had they built up and accumulated, maybe we would have had a fifth rocky planet. But who knows? In the future that still could happen potentially. But for now, just 4. Ceres is the largest asteroid. It is considered a dwarf planet just like Pluto, and yeah, it's just kind of a fun fact. So comets, how are those different from asteroids? Comets are chunks of ice with elongated orbits around the sun. The tail, which you see in that left picture, is produced when the ice is vaporized by a near-sun orbit. So when these things of ice are traveling through space, and they usually have very strange orbits, they have these elongated orbits, you'll see that there's this huge tail, and it's enormous, and it's also very pretty. So when these things are moving, that tail doesn't actually show necessarily where they're moving, it just shows where the sun is. So the sun is on the left-hand side of it, making this tail go out to the, I suppose, right-hand side of that picture. Halley's Comet is the most famous comet that we have, and it has a 76-year orbital period, so usually people see it about once in their lifetime. And taking a look at the different parts here, you've got the actual chunk of ice, which we call the nucleus, the little envelope of gases that go around it, this like really glowy covering that almost makes it look like it's on fire, we call it the coma. And then, as we said before, we have the tail going behind it, and that can be as long as 1 AU. And remember that 1 AU is the distance from Earth to the sun, so that's really, really big. So these things are traveling through space aimlessly. Why do we care? Well, meteoroids are the name for any of these rock or ice fragments that are traveling through space and potentially could hit into us. So meteors, that is what happens to meteoroids that actually end up passing through our atmosphere. And when they do that, they usually go on fire because there's an enormous amount of friction once they actually start rubbing against all that air at the speeds they're going, and so they go on fire and then sometimes explode. And then meteorites, these are the meteors that don't explode, that do go on fire but still make it to the ground, and so they're usually made of stone, or they can be very, very heavy metals, but that is what we would call a meteorite. And so interesting things with this, right? The big one is the impact event 65 million years ago, fossil evidence for the extinction of dinosaurs, and 65% of all species due to a comet or asteroid impact. And we actually do know, pretty much know, the impact site, which is just partially in Mexico, partially in the Gulf of Mexico. It's called the Chicxulub crater. It's enormous, but it's pretty cool, so you can definitely check that out if you're interested. Then, in terms of where a lot of this space debris is, we had mentioned that between the rocky and the gas planets we have a lot of the different rocky material, But in terms of comets, there's two places where a lot of those exist. So the first one is the Kuiper Belt, which is just beyond Neptune. You can see on the left. And then outside of the Kuiper Belt, if you go really far away, but still within our solar system, there's a cloud, the Oort cloud, which surrounds us in a dome, and that is trillions of miles wide. So we've got these two layers where comets have accumulated. So we certainly don't only have Halley's Comet. We have a whole bunch of icy material that exists out there. So here's some pictures. Again, when this is going through the sky, we would call that a meteor. And as soon as it hits, this one broke through a frozen lake. As soon as we have it on Earth, we call it a meteorite. So, folks, here is a video that you should definitely watch. These are all different video shots of the same meteor that occurred in 2013, and Russians all have dash cams on their cars, so they got a whole bunch of great footage of what this looked like, and it burns almost as bright as the sun. So it's really pretty neat to watch that footage. So go into the PowerPoint, or the Google Slides rather, and go take a look. So of course, meteors, meteorites, meteoroids, definitely popular in fiction, from video games, anime. People like it. It's interesting to think that our daily life, we don't really think about stuff in space colliding with us too often. But if there's a big enough thing, it becomes a big enough problem. Definitely, humans are fascinated with it. Also, good movie to watch, Armageddon. Classic. So, another video if you're interested in the Google Slides. That brings us to the question. While traveling around the sun, why does a planet not fly off into space? So, pivoting from the material that's out there to looking back at us. So, why don't we just fly off into space? So what is it that makes it so that we're stuck kind of in this cycle? So there are three laws. We're going to talk about one of them, the main one today, in this video. And they are all laws of planetary motion made by Johannes Kepler. He was somebody who liked to study planets and whatnot. So, of his laws, the first law is the orbit of planets around the sun are elliptical, which makes those shapes you see at the bottom of your screen. Those are called ellipses, with the sun at one fixed point called a focus. And there are usually, for these things, two focuses, so we say foci. This gives us, with an equation, which is on the front page of your reference table, eccentricity, which is the shape of an ellipse. So there is no orbit that's actually like the red orbit, right? 0.0 is a perfect circle. There are no perfect orbits. Even the best, most perfect orbit, well, I guess it's not necessarily best, but the most near circular orbit is still off in our solar system with a, 0.007? It's very close, but it's not perfect. So even that, even the one that's super close, is still technically what we call an ellipse. So to figure out this number, right, on the bottom you can see that there are the numbers for eccentricity. And remember that it goes from 0, a circle, to 1, which would be a straight line. There is an equation that gives you those numbers, which uses the foci, so these two focuses, these 2 points within the orbit, and then you divide that by something called the length of the major axis. So that's what we're going to look at right now. This is something that may come up on the lab practical, the physical portion of the Regents, should we still have it this year. So usually with the Earth Science Regents, there's the 80 or so questions, and then there's also a lab part where you have to do hands-on lab activities. This happens to be one of them, is making ellipses and then calculating their eccentricity. So if you look at some pictures, you can see that the foci can either be close together near the center or further away. And if you look, the one that is closer together makes more of a circle, and when the foci are far away, it ends up making more of a drawn out ellipse. And again, E is closer to 1 in the left picture, so it's more circular, and E is going to be closer, or sorry, E is close to 0 in the left-hand picture, so it's more circular. E is close to 1 in the right-hand picture, so it's more elongated. Here's just another picture to showcase that. When these two little blue things, the foci, are close together, it makes more of a circle. That's low eccentricity. And when they're spaced out further, you end up getting that elongated shape. Also, this does affect their motion. If you are in an elliptical orbit, chances are you move slower when you are far away. Follow the pink here. Slow on the far side away from the sun. And then as it comes closer to the sun, you'll see that it accelerates and slingshots around. That is very different than the more circular orbits that are a little bit more constant with their speed. But going back to eccentricity. So how do you calculate it? Well, it is d for distance, which is between these two dots. So these are the two foci. And remember, the sun is at one of these points. The other point's actually empty, but that's just a mathematical thing. So the sun is at 1, and the distance between those foci divided by this. So the length of the major axis is a line that goes through from side of the ellipse to the other side, and it has to cut through both foci. So there's only one way you could draw it. But you take the distance between the foci, you take this distance from one side to the other, and when you divide, that will give you your eccentricity. So if you set it up as an equation, E is equal to d over L, and here's some fake numbers. Let's just say it was 2.0 over 21.7. So that's another important thing. The eccentricity is always going to be small number over big number. And when you get your eccentricity, you always have a decimal and then 3 digits behind it. So you always go to the nearest thousandth. So you'll get, 0.452 or 0.223. And if you got something that was perfect, like let's say you only had 0.5, you still need to write 0.500. And so, what is the eccentricity of an ellipse in which the distance between foci is 2 centimeters and the length of the major axis is 5 centimeters? So going into this word question, you'd look and say, okay, I know my equation. It's the distance between foci divided by the major axis. So you would get 2, which is the distance between the foci, divided by 5. 2 over 5 gives you, calculate it, pause the video here. Alright, so hopefully you calculated that, and that would be 0.4. But can you write it as 0.4? No, 0.400. Here's a thinking question. When the distance between the foci of an ellipse is increased, the eccentricity of the ellipse will do what? What's happening to that number if you increase the distance between the foci? So as you're pulling those foci apart, what is happening to eccentricity? It should be increasing. As the foci are further apart, you will get a more drawn out shape. So that's it for today. We will be talking about the other 2 laws tomorrow, and that's it. So have a good day.